Hello, and welcome everyone to this podcast. In this podcast, we're going to talk about the material from Chapter 3, and this covers why water is important or essential for life. You often hear people say, where there is water, there is life. If you watch any of NASA's exploration of space, we know that when they explore planets like Mars, they look for water, because we know if there's water that there's a possibility that could be life there, or at one time there could be life. And that's because the properties of water allow life to form and to exist. So we could sum it up by saying all organisms require water. Cells, which are the fundamental unit of life, are about 70 to 95% water. Most cells, in addition to being made up of mostly water, are surrounded by water. Biological reactions require water. So we can see that water is an important part of life, an important part of cells. But why is it important? To understand that, let's look at the properties of water. And there are 4 key properties I want to talk about today. So let's spend some time talking about the properties of water to help us understand why water is so important for life. We're going to talk about 4 properties. The first will be cohesion of water and adhesion. 2 really important properties of water. The next one will be water's resistance to temperature change. The third will be water's ability to expand upon freezing. And the last one we're going to talk about is water's versatility. As a solvent. That is, its ability to dissolve many things. Let's begin with adhesion and cohesion. Before we begin our discussion of cohesion and adhesion, let's remind ourselves what the water molecule looks like and how it participates in hydrogen bonding. Remember that the water molecule, because of the way it forms, is partially positive at the hydrogens and partially negative at the oxygen. Because of that, it can bind to, the hydrogen of the water molecule can bind to negative or partially negative atoms of other molecules. So for instance, this hydrogen could bind to a nitrogen molecule that contain hydrogen molecules attached to it, like so, where the hydrogen molecules here are partially positive and the nitrogen is partially negative. We say that between this partially positive and partially negative atoms that we form a hydrogen bond. We also talked about how water can bind to itself. Say for instance, it could bind to a partially negative oxygen of this water molecule to this partially positive hydrogen atom of this water molecule. Again, that would be a hydrogen bond. Now these hydrogen bonds, remember we said they're not very strong. Individually they're pretty easy to break. However, collectively, when you have a whole bunch of them together, they're very strong. So with this reminder what hydrogen bonds are doing with the water molecule and with other substances, let's now define cohesion. Is the ability of water to bind to itself. So here would be an example of cohesion, where this water molecule is binding to this water molecule. Next, let's define adhesion. Adhesion, for this purpose, means water's ability to hydrogen bond to other molecules. So for instance, the hydrogen bonding between this water and this molecule here is an example of adhesion. A great example of how cohesion and adhesion work in a biological process is to think about a tree. It could be any plant, but I'm going to talk about a tree because trees are tall and it kind of illustrates this phenomenon a little bit better. So we've been taught a long time ago, I suppose, that water hits the ground, it's absorbed by the roots, and the roots will take the water up the tree and into the leaves. And it does so because of these water conducting cells that move it up the tree. However, what is it that allows the water to move up as opposed to falling back down because of the forces of gravity? To a large extent, it has to do with the properties of cohesion and adhesion. Remember, cohesion will hold the water molecules to each other. And since the water molecules are going to be held together, as they're moving up this tree, they're held together kind of like a network of chains. So these water molecules, let me keep it in blue, the same color here, will be held together. So as one water molecule moves up, it's attached to the next one, the next one, the next one, the next one, and so on. So they all move together. Much like if you had a chain, all the links together, you pull that chain, you have to pull the bottom chain link if you pull the top chain link. They're connected. And as water evaporates from the leaves, that allows more water to come up here. So it's this kind of tugging of the water molecules. As it's leaving, it brings the next water molecule up. Let me say that again. As one water molecule leaves through the leaf, say, the next water molecule is tugged into the next position. Because remember, they're held together because of the property of cohesion. So what does adhesion have to do with this? Remember, the other property is that water can hydrogen bond with other substances. In this case, it's going to be with the cell wall. So as water is being tugged up, it's also important that gravity doesn't pull it back down. And one way that this is accomplished is that the water molecules will bind to the cell walls here, all the way up here to the cell walls of the leaves, and so forth. And that will help resist the pull of gravity. I didn't write this word down, but I said it, so I want to make sure I write it down. Because if you're asked this question ever, you would want to make sure you include these three words and the description of it. The water is held together and is pulled up, much like a chain would be pulled up, because of cohesion, the water molecules binding to themselves. As one water molecule evaporates, it pulls the next water molecule into position. What's preventing the water molecules from moving back down is largely due to adhesion, the water molecules binding to the cell wall. I want to erase this, and I want to talk about one other important property that comes out because of cohesion. And this other property is called surface tension. We can think of surface tension as the measure of how difficult it is to stretch or break the surface of a liquid. Every liquid has a defined surface tension. Some of it is stronger than others. For instance, water, if you think of this body of water here, and all the water molecules below it, because of cohesion, because of the water molecules next to each other on the surface binding to each other, but also binding to each other as you move down the layers of this water, creates an incredibly strong bond. Now, obviously, if we jumped in here, that would be enough to break the surface. But we've all seen, probably, lakes or ponds where we will see bugs, like like some kind of spider that might be able to walk right on the surface of the water. It's not because the spider is super light. It's largely because of the very high surface tension of the water that prevents this spider from falling through the water. Now I'd like to talk about the second property of water that's important for life, and that is its resistance to temperature change. Alright, I'd like to talk about the second property of water that's important for life, and that is water's resistance to temperature change. This is largely due to water having a relatively high specific heat compared to other substances. High specific heat really is defined by how much heat or energy a substance needs to gain in order for its temperature to change. So you've probably seen an example of this in your own life. For instance, if there's a large body of water here and it's, say, December, it's very cold. The temperature outside is cold. The water is cold. However, when maybe May comes around, we might want to say June or July in case you're in the UP, but in May usually the temperature does get a little warmer. You'll have the same body of water here. I'll try to draw about the same. The temperature outside gets warmer. And because of the high specific heat of water, the water doesn't get as warm as the air temperature. It's maybe not as cold as it used to be. It's cooler than the temperature outside. Because water takes a lot of heat to be absorbed before the temperature of the water will change. Now maybe by June or so, when the warm air is warm outside, you'll see the water getting a little warmer as well. But it takes a lot of time and a lot of warm air and hot air before the water in this big body will change to a warmer temperature. Now, if you were dealing with a substance that wasn't water, say ethanol, that has a lower specific heat, then what would happen is that when the temperature outside became warm, the ethanol would also become warmer too, much faster. Okay, so water has this resistance to change its temperature because of high specific heat. But why does it matter? Well, it matters for a few reasons. We can mention a few things here. One is that high specific heat allows the temperature to stabilize in marine environments, in the ocean. Because the temperature of the water doesn't change as quickly as the air temperature, there can be a fairly constant temperature of the ocean. This is important for the animals that live in the ocean, so they don't have to fluctuate their temperature as rapidly as the air does. Another important thing to remember is that organisms are mainly made of water. Because of that, organisms are better able to resist changes in their own temperature due to fluctuations of the temperature around them, as opposed to if they were made of a different kind of liquid, say that of ethanol. Ethanol, a liquid that much more rapidly adjusts to the temperature around it. Now, another term related to water's resistance to temperature change is this term evaporative cooling. The basic idea behind evaporative cooling is that as a liquid evaporates, the surface where it was released from cools down. And the reason for this is that the hottest molecules, that is, the molecules with the greatest kinetic energy, are the ones most likely to leave as gas. When the hottest molecules leave, what's left behind are the molecules that are a little cooler. And so that allows the surface to cool down. We can go back to a description here of a pond, of course filled with water. And remember, we talked before about how in a larger body of water like an ocean, how the temperature remains stable. The same is true here, and let's explain why using this evaporative cooling. As the heat comes down from the sun and warms the air, it also warms this water. The water molecules at the surface here are going to get hotter. They're going to have a lot more kinetic energy because of that. And because of that extra kinetic energy, those hotter water molecules, so let's say these hotter water molecules, they'll leave the surface. When they leave, the part of the water that remains is the colder part. So this will happen continuously throughout the day as the warm air hits the water. Due to the increased kinetic energy of these hotter water molecules, they'll be released. What remains behind are the cooler water molecules. So let's talk about how this can influence living organisms. I'm just going to draw a human because it's easier for me to draw, but this is true of any living organisms, from plants to humans and anything else. When the sun warms the air, we become warm as well. Now, we can cool down in many different ways, and you'll learn about some of those ways in this class, but also as you progress through the biology curriculum, you'll learn about other mechanisms we use. But let's talk about how evaporative cooling can cause us to cool down. Just like this pond over here, we're made of mostly water. When we become hot, what happens is those water molecules in us, they will also warm up. And as they are released from our body, say from our arm skin here, they are released as water vapor. The part of the water that is released first as this vapor are going to be the hotter water molecules, just like the pond here. What's left behind are the cooler water molecules, or the cooler substances of our skin, which allows us to remain cooler. This is one of the reasons why when it's really hot and really humid outside, so if it were a very humid day, meaning there's a lot of water molecules in the air, it's much harder for us to cool down by evaporative cooling because it's harder for us to release a lot of water vapor from our skin into the air, which is already highly concentrated with water. So that's why on these humid days we feel so uncomfortable. It's because we are ineffective or less effective at evaporative cooling. Alright then, that concludes the first two of the 4 properties of water that make it essential for life. I'm going to go ahead and stop this podcast now, and then on the next podcast I'll include the last 2, as well as our discussion of acids and bases and pH. If you have any questions about this material, please make sure you come see me, and if not, I'll see you in class. Bye.